Okay, welcome to our second PowerPoint for this ISU unit. This is for section 9.2. Hopefully you've had a look at it. And I'm just going to walk you through it using examples and pictures right from the textbook so you have some idea of what's happening. Okay, so we are always going to be looking at what are called redox reactions. In a redox reaction, something was oxidized and something was reduced. That's why we call it a redox reaction. Therefore, something gained electrons and something lost electrons. Now, that means if we're counting electrons, a reaction is not going to be balanced the typical way we used to do it in grade 11. We actually have to balance for the atoms, but we also have to balance for the number of electrons transferred. So if something gains 5 electrons, we have to lose 5 electrons. That is super important. As a result, you're going to be balanced for charge, and we're going to have to balance for hydrogens and oxygens, and we're going to have some tricks to be able to do that. We're going to use water to balance our oxygens, because these redox reactions typically take place in water, so H2O has an oxygen. And typically they take place in acidic reactions, so we can use H ions or hydrogen ions to balance our H's. And if we take place in a basic solution, we are going to use hydroxide ions. So we're going to, in this section, learn how to balance a redox reaction. There are 2 methods. I don't particularly care which way you use. They're the same. Half reactions is a little bit easier for when you're doing batteries and cathodes. So you will want to familiarize yourself with it, especially for next year for your electrochem. But we'll start with what's called the oxidation number method. It's a little bit shorter and straightforward, but they both are pretty much the same thing is happening in both types of approaches. So here's the steps for balancing redox reactions. You should write them down or put them in your notes so that you can follow along. So what we're going to do is first write down our basic equation, and we are going to write oxidation numbers for everything. Make sure your oxidation numbers are right. If they're not right, everything's going to be messed up. You want to make sure that we balance the number of electrons that got transferred. So if we transfer 5 electrons, we need to multiply the number of atoms that are involved, so we have the right number of electrons transferred. We're going to then, this is an important step, we're going to have a look and make sure that all the other atoms are balanced. Sometimes you might have to just put a 2 in and double something to make it balance, especially if it's not involved in the electron transfer. Then you may find that you have more oxygens on one side than the other. So if you do have that, once everything is done, if you have oxygens that are not balanced, I want you to add water to the side that needs more oxygens. Of course, when you add water, you're also adding hydrogens, right? Because you're adding H2O. So you're going to be adding waters, and then if you need to balance hydrogens, you are going to use hydrogen ions to balance hydrogen. That is if your reaction is happening in an acidic environment. If it's happening in a basic environment, you are still going to use hydrogens first to balance it. Pretend you're in an acidic environment. And then you're going to have one extra step. You're going to add OHs, the same number of OHs to each side that you added the H's to. And I'll show you exactly what I mean there. Okay? So let's have a look. Let's try. So I'm going to go away from this screen, but you can open up to page 608 to follow along as we try to balance. So here is an equation. You would not be able to balance this through your grade 11 methods because it says MnO4, the manganate ion, plus iron ion gives me manganese and iron. Oxygen has disappeared. So we have to use our oxidation number method. First of all, we want to identify, is this a redox reaction? And you will know if it's a redox reaction because the oxidation numbers will change. If the oxidation numbers of everything doesn't change, it wasn't a redox. So step 1, assign oxidation numbers. MnO4, oxygen is always -2. All right, well, there are 4 of them, so I have to account for -8. I've got, so my oxygens have a total electron bookkeeping of -8. And I have a manganese here. What does my manganese have to be to leave this -1 charge? Well, my manganese will need to be +7. So that's how I figure that guy out. Iron here is a +2 charge. It's just going to be its oxidation number will just be its charge. Manganese will just be its charge. And here, iron will just be its charge there. So let's go through this and identify if something was oxidized and if something was reduced. So it looks like manganese went from +7 to +2. So +7 to +2, that represents a gain of 5 electrons for every, manganese ion. Okay. So for every manganese ion, it's 5 electrons. Now iron went from +2 to +3. It got more positive. Therefore, it lost 1 electron for every iron atom. Now, we can't have a reaction where manganese is reduced, gains 5 electrons, but iron only loses 1. They have to be balanced. So how do you make this even? So what we're going to do, I'm just going to change the color here so it's a little bit more obvious. We're going to multiply this half reaction by 5. And if you want, you can say this reaction by 1, so that the number of electrons is balanced. So if I multiply this reaction by 5, I have to put a 5 here and a 5 there. And that's going to make my electrons completely balanced, because now I multiplied it by 5, that's 5 electrons. This one I multiplied by 1, that's still 5 electrons. So my electrons that are transferred are balanced. Okay, so I'm good. I've got this. Now, the only thing that's left is to look at oxygen. On my reactant side, I have 4 oxygens, and on my product side, I have no oxygens. So I'm going to go ahead and add 4 waters. Now my oxygens are balanced, but hopefully you see I've got a new problem. I have introduced 8 hydrogens over here. So notice this is happening in an acidic solution, which means I have hydrogen ions available. So on this side of the reaction, I'm going to add 8 hydrogens. And I'm done. Am I balanced for atoms? Yes, 1 Mn, 1 Mn, 5 Fe's, 5 Fe's, 8 H's, 8 H's, 4 O's, 4 O's. I'm good. Am I balanced for total charge? 8 plus and 1 minus is 7 plus. And this is 10 positive. So 7 positive and 10 positive is a total of 17 positive charge. On this side, I have Mn 2 plus, and 5 times 3 is 15. I have a total of 17 positive charges on this side. So they're balanced for charge. Did my electrons balance? 5 were lost and 5 were gained. Yes, I'm good to go. This reaction is balanced. 8H plus MnO4 minus 1, 1 minus I meant, plus 5 Fe yields Mn2 plus 5 Fe3 plus 4 H2O. That's all there is to it. You have to practice. There's lots of tricks and tricky ones, but you just have to practice and try different ones. There's a lot of great ones to try in the textbook. We're going to do another one, but this time we're going to make it a basic solution. So there's one extra step for a basic solution. So let's start. I've got it written here. You first balance the H's on each side using H+, then you add the same number of OH's to each side. The H's and the OH's you will gather up and form water, and then you will reduce any extra waters that are on either side. So I'm going to start with my oxygen. My oxygen, I'm going to do it in red. I like oxidation numbers to be in red, and I always like them on the top, is -2. There are 3 of them. That's a total of -6. My iodine will have to be +5. because that +5 and the oxygen total of -6 leaves a -1 charge on this ion. So that's what I have there. On C2O4, each oxygen is 2-. Of course, there are 4 of them. That's a total of -8. That means my copper, my total carbons have to be +8. There are 2 of them. So each carbon will have to be +4. Iodine is going to be the same as its charge, so it's going to be -1. Oxygen will be 2- here. 2- times 2 is -4, and therefore each carbon is +4. Okay, so we've got 3 things here. I've got oxygens, iodines, and carbons. The only things you're going to be paying attention to are the things where whose oxidation numbers changed. Notice that carbon was +4 here and +4 here. Its oxidation number didn't change. So you don't care about the oxygen here. Oh, I forgot the 2-. Oh, man.